Okay, the topic for today is transformer. So I don't know what image you have when you think of the idea of transformer. But it does sound familiar, right? Well, transformer has got to do with the two coils that you see here in this. Now, let's take a look at how it actually works. Okay, so when you see these two coils, okay, so I'm just going to move this a little bit nearer. Alright, so we have these two coils. The one on the left, we call it the primary coil, and the one on the right, we call it the secondary coil. Alright, so nothing much is happening here. There's only a DC supply in the primary coil. Now, however, if you notice, I'm going to reverse the polarity of the DC circuit here on the left, and let's see what happens. Okay, so you can see there's a flicker on the lamp. Flicker on the lamp again. So when I reverse the polarity of the DC supply, there's a flicker on the lamp. So what happens is that when I reverse the polarity of the DC supply on the left, there is also a change. I'm causing a change in magnetic flux in the primary coil on the left. And because they are so near enough, the secondary coil is also within the magnetic flux of the primary coil, and this causes a change in magnetic flux in the primary coil as well, and therefore there's an induced EMF as well as induced current in the secondary coil. So this is still related to Faraday. In fact, this is the application of what we learned in electromagnetic induction. Okay, let's look at the idea like up close. Now, let's recall again, this is primary coil, and this is the secondary coil. So usually we will have this an electrical supply. All right, so we will supply electrical supply to the primary coil. Now, if you notice earlier, okay, when it was a DC supply, I have to do the reversing, right? But let's say, for example, I'm going to put an AC supply on the left coil. I wouldn't need to do the reversing because, right, an AC supply in the primary coil would naturally cause the magnetic flux in the primary coil to change constantly, and therefore the magnetic flux inside the secondary coil will also constantly change, and that will automatically induce a current or an EMF also in the secondary coil. So normally we would like to have the primary coil be supplied with an AC supply instead of DC, then we don't have to turn it on and off and reverse the polarity all the time. Okay, now, so what happens is that, just a quick summary, so when it is an AC supply on the primary coil, there will be a changing magnetic flux in the primary coil. So when there's a changing magnetic flux in the primary coil and the secondary coil is near enough, so the magnetic flux inside the secondary coil, which is due to the primary coil, is also changing. So we also have a changing magnetic flux here. So whenever there's a changing magnetic flux in the coil, then there will be an induced EMF. And in this case, because it is a closed circuit, we're going to have an induced current. Okay, let's go a little bit more in depth to see how it actually works. Now, a transformer, a simple diagram would actually look like this. Now, a transformer must have a primary, so let's identify the primary coil. Okay, so I know it's primary coil because we're supplying an AC supply on this side, and the other side would be a load, like a light bulb or something. So this is your secondary coil. Now, there's an additional thing that you see over here, this gray color rectangle thing. Do you want to guess what it is? Well, it's actually a soft iron core. So recalling what you learned in magnetism, what do you think the soft iron core is for? basically is to concentrate the magnetic field lines, correct? Okay, I'm glad you got it. So that it will be very effective. So when you have a changing magnetic flux in the primary coil, then there will also be a changing magnetic flux in the secondary coil. So the field lines within these two coils are concentrated. Okay, so then it will be more efficient in this way. Right, now how does this actually work? So why do we have to induce current and induce EMF, which is so troublesome? Now we have this induced EMF here. Okay, so there are times whereby I may not want a very large EMF, or I want a smaller EMF. Okay, so this transformer allows us to do that. Okay, because what is the concept behind it? So the ratio of the voltage at the secondary coil, Vs, to Vp depends on the ratio of the number of turns at the secondary coil to the number of turns in the primary coil. So fundamentally, the concept or the ratio is like this. So the ratio of the secondary coil to the voltage at the primary coil will be equals to the number of turns at the secondary coil and to the number of turns in the primary coil. And this tells us that if we have a larger number of turns in the secondary coil than the primary coil, we're going to get a larger induced EMF, which means something like this. So if we have a larger voltage, if we want a larger voltage induced at the secondary coil, we can turn more number of turns at the secondary coil, right? So then in this case, I'm going to have a larger induced EMF in the secondary coil. And this is what we call a step-up transformer. So we have a larger induced EMF in the secondary coil. If we want a smaller induced EMF in the secondary coil, then it would be smaller or lesser number of turns as compared to the number of turns in the primary coil. So this is what we call a step-down transformer. Okay, now is there such thing as a free lunch? How can we step up and step down as we like? So what is the main concept that governs here? Right, so physics is always into conservation of energy. So basically, this transformer will still always obey the conservation of energy, which is conservation of power, which is energy per unit time. Okay, so the power supplied at the primary coil must be equals to the power supplied at the secondary coil. Which means that the current in the primary coil multiplied by the voltage at the primary coil is equals to the current induced at the secondary coil multiplied by the voltage induced or the EMF induced at the secondary coil. So there's really no free lunch here. What happens if it is a step-up transformer? Which means that if it's a step-up transformer, that means my voltage at the secondary coil will be higher. And that means that my current would be smaller. And this current here will be larger and smaller voltage. So this is the situation of a step-up transformer. Okay? And if it is a step-down transformer, which means that my voltage, oops, I should put a P here. So if it is a step-down transformer, which means the voltage at the primary coil would be larger than the voltage at the secondary coil. That means the current at the secondary coil, the induced current at secondary coil, would be larger than the current at the primary coil. So this is the scenario if we have a step-down transformer. Okay, so that's why there's actually no free lunch. So if we want a step-up situation, we will actually get a smaller current induced in the secondary coil. All right, so this is the concept of transformer, and later on we'll see how it can be applied. Thank you.